let's continue. Okay. I think previously we are in the where is it? Persistence. Okay. When we are writing a C program, we might use an editor, right, to create and edit the C file, and then we might use the compiler to turn the source code into an executable. Okay, so basically we are using main.c input the text editor and the compiler. You can see how files are shared across different processes. First, we make create a file that serves as input to the compiler, and then the compiler uses that input file to create a new executable file. In many steps, the compiler calls for the file. Thus the new program is born. Okay. Okay, this is an example. We are opening or creating the file. If the file does not exist, and this one, is this right only? Maybe. I'm not sure about this one. Let's look at some code. The program make 3 calls. First call to open function or system call to open the file and create it. Second one calling to write function to write some data to the file, and then the last one is close, this one, to close the file, indicating the program won't be writing any more data to it. What which then handles the request and returns some kind of error code to the user. Okay, doing so request, issuing input-output request to the underlying storage device to edit and read existing structure or update them. It requires deep knowledge of low-level device interface and its exact semantics. Fortunately, the operating system provides a standard and simple way to access the device through its system calls. Thus, the operating system is sometimes seen as a standard library. Because there are many more details how devices are accessed and how file system manage data persistently atop said device. For performance reasons, most file systems first delay such writes for a while, hoping to patch them into a larger group. To handle the problem of system crash during writes, most file systems incorporate some kind of intricate write protocol, such as journaling or copy on write. Carefully ordering writes to text to ensure that if a failure occurs during the write sequence, the system can recover to reasonable state afterwards. For the copy on write, if I understand correctly, we create a duplicate of the file first, and then writing on this duplicate, and then replacing the original with the duplicate if the write already finished. But if the failure occurs, then we didn't do anything to the original file, if I understand correctly. I'm not sure about the journaling in here. Is it maybe something like log? Maybe. Okay. The system can recover to reasonable state afterward. To make different common operations efficient, file systems employ many different data structure and access methods, from simple list to compact with trees. This one. If all of this doesn't make sense yet, good will be talking about all of this quite a bit in the third part or the third piece of this book on persistence, where we will discuss the files and input-output in general, and then text rates. Okay. Let me also open the table of content. Kind of forgot. I did an array of inexpensive text. Well, now it might be expensive. I mean, yeah, I'm not sure what inexpensive in here related to. And file system encrypted tile. Okay, let me read this. At the file driver is some code in the operating system that knows. Yeah, I'm currently on introduction. Where is it? This one on persistence. We are still early in the chapter. At the file driver is some code in the operating system that knows how to deal with specific device. We will talk more about the device and the device driver later. Okay. The crux of the problem, how to store data persistently. The file system is the part of the operating system in charge of managing persistent data. Okay. What techniques are needed to do so correctly? What mechanisms and policies are required to do so with high performance? How is reliability achieved in the face of failure in hardware and software? Right. Okay. The file driver can run in kernel or user space also. It's just regular code. Oh, okay. That makes the device do stuff. Oh, nice info. I didn't know that the device driver can run in user space too. Okay. Now let's continue to design goals. So now you have some idea of what an operating system actually does. Okay. It takes physical resource such as a CPU, memory, or disk, utilize them. Take some physical resource. Okay, and virtualize them. Alright. It handles tough and tricky issues related to concurrency. It stores files persistently, thus making them safe over the long term. Given that we want to build such a system, we want to have some goals in mind to help focus our design and implementation and make trade-off as necessary. Finding the right set of trade-off is a key to building system. You want to have some goal, okay, in mind, implementation, and make trade-off as necessary. Okay, so we will be trying to build the system. Oh, interesting. Okay, one of the most basic goals is to build up some abstraction in order to make the system convenient and easy to use. Abstractions are fundamental to everything we do in computer science. Abstraction makes it possible to write a large program by dividing it into small and understandable pieces to write such a program in a high-level language like C without thinking about assembly. To write code in assembly without thinking about logic gates. Oh, and to put a processor out of gates without thinking too much about transistor. Okay, abstraction is so fundamental that sometimes we forget its importance, but we won't here. Alright. Thus, in each section, we'll discuss some of the major abstractions that have developed over time, giving you a way to think about pieces of the operating system. One goal in designing and implementing an operating system is to provide high performance. Another way to say this is our goal is to minimize the overhead of the operating system, virtualization, and making the system easy to use are well worth it, but not at any cost. Thus, we must strive to provide virtualization and other operating system features without excessive overhead. These overheads arise in a number of forms. extra times, more instruction, and extra space in memory or on disk. Oh, extra time because more instruction. Okay, and then extra space, memory or in disk on disk. We'll seek solutions that minimize one or the other, or both if possible. Perfection, however, is not always attainable. Something we will learn to notice and will appropriate tolerate. Okay. Another goal will be to provide protection between applications as well as between the operating system and application. Protection. Okay. Because we wish to allow many programs to run at the same time, we want to make sure that the malicious or accidental bad behavior of one does not harm others. We certainly don't want an application to be able to harm the operating system itself, as that would affect our program running on the system. Protection is at the heart of one of the main principles underlying an operating system, which is that of isolation. Right? Isolating process from one another is the key to protection and thus underlies most of what an operating system must do. The operating system must also run non-stop. When it fails, an application running on the system fails as well. Because of this dependence, operating system often strives to provide a high degree of reliability. As operating systems grow ever more complex, sometimes containing million lines of code, building a reliable operating system is quite a challenge, and indeed, much of the ongoing research in the field, including some of our own work. Okay, this is the reference. We will take a look at this later on. Building a reliable operating is quite a challenge, and indeed, much of the ongoing research in the field, including some of our own, focus on this exact problem. Other goals make sense. Energy efficiency is important in our increasingly green world. Security, an extension of protection. Okay. Against malicious application is critical, especially in these highly network times. The mobility is increasingly important as operating systems are run on smaller and smaller devices. Okay. Depending on how the system is used, the operating system will have different goals and thus likely be implemented in at least slightly different ways. However, as we will see, many of the principles we will present on how to build an operating system are useful on range of different devices. Okay. Alright, that is the design goal. Looks like we will be kind of designing a simple operating system. Maybe. Okay, let me write this. Some of you may object to call C a high-level language. Remember, this is an operating system course though. Well, we are simply happy not to have to code in assembly all the time. Okay. Let's continue to some of the history. Before closing this introduction, let us present a brief history of how operating system developed. Like any system built by humans, good ideas accumulate in operating system over time. A minute. It's been cold lately in here, so okay. Like any system built by humans, good ideas accumulate in operating system over time. As engineers learn what was important in their design, here we discuss a few major developments for a richer treatment. Oh, Fritz Hansen's excellent history of operating system. Okay. Early operating system, just libraries. Oh, the early operating system is just libraries. Okay. In the beginning, the operating system didn't do too much. Basically, it was just a set of libraries of commonly used functions. For example, instead of having each programmer of the system write low-level input-output handling code, the operating system would provide such API and thus make life easier for the developer. Usually on this old mainframe system, one program ran at a time, as controlled by a human operator. Most of what you think a modern operating system would do, deciding what order to run jobs in, was performed by this operator. Oh, the human operator. Okay. If you were a smart developer, you would be nice to this operator, okay? So that they might move your job to the front of the queue. This mode of computing was known as batch processing, as a number of jobs were set up and then run in a batch by the operator. A number of jobs were set up and then run in a batch by the operator. Computers as of that point were not used in an interactive manner because of cost. It was simply too expensive to let a user sit in front of the computer and use it, as most of the time it would just sit idle. Then, costing the facility hundreds of thousands of dollars per hour. Okay. Beyond libraries protection, in moving beyond being a simple library of commonly used service, operating system took on a more central role in managing machine. One important aspect of this was the realization that code run on behalf of the operating system was special. It had control of the files and thus should be treated differently than normal application code. How is this? Well, imagine if you unload any application to read from anywhere on the disk. The notion of privacy goes out of the window. Any program could read any file. Thus, implementing a file system to manage your file as a library makes little sense. Instead, something else was needed. Thus, the idea of a system call was invented. Okay. Listen to a more hands-on role in managing machine. Code run on behalf of the operating system was special. Normal application code. Normal application code. So we are trying to separate between the normal application code and the operating system code. Is that it? Maybe the idea of a system call was invented, pioneered by the Atlas computing system. Okay, this is the reference. Instead of providing operating system routines as a library where you just make a procedure call to access them, the idea here was to add a special pair of hardware instruction and hardware state to make the transition into the operating system a more formal control process. The key difference between a system call and a procedure call okay. Is that a system call transfer control jumps into the operating system while simultaneously raising the hardware privilege level. Okay. Wait a minute. What is procedure call again? So, in transfer control, is procedure call also transfer control into the operating system. User application run inward is referred to as user mode, which means the hardware restricts what application can do. User mode, the hardware restricts what application can do. For example, an application running in user mode can typically initiate an input-output request to the disk, access any physical memory page, or send a packet on the network. An application running in user mode can typically initiate an input-output request to the disk, access any physical memory page, or send a packet on the network. When a system call is initiated, usually through a special hardware instruction called trap, the hardware transfer control to a pre-specified hardware trap. The hardware transfer control to a pre-specified trap handler. The operating system set up previously and simultaneously raise the privilege level to kernel mode. Okay. In the kernel mode, the operating system has full access to the hardware of the system and thus can do things like initiate an input-output request or make more memory available to a program. Can do things like initiate input-output request to the program. Full access to the hardware of the system and do this thing. When the operating system is done servicing the request, it passes control back to the user via a special return from trap instruction. It refers to user mode while simultaneously passing control back to where the application left off. I'm still not sure the difference between system call and procedural call. Let me check. Is procedural call also called library call? Is that it? Let's take a look at this. System call are slower to execute. Okay. Local processor. Oh. Okay, I need to know what procedure call is. The procedure in execute a specific program or perform certain tasks. Differs from a function, a routine, or a method. Are used in various programming languages with the same fundamental role of allowing a programmer or a developer to call them multiple times within a program. Improve code efficiency and reusability. Classic linear program. Similarly, let me check. Print a point in the polytope. When this function has largest or smallest value if such a point exists, that can be expressed in linear relationship. Okay. Additionally, maintaining solution in complex process, lacking flexibility and refinement is extremely difficult. Automatic development, however, procedure with an ID and a partition of code. Okay. So maybe system call and procedure call also transfer control, but procedure call didn't raise the hardware privilege level. Is that it? Monitoring. maybe okay, transfer control from the current process to another. Okay. List of parameters along with the procedure call. After successful execution, control resume to the initial procedure invoked, and the program continues its execution. Good morning, ping pong, boing. Welcome. We are currently on this one, chapter 2, in the section some history, and I'm kind of curious about the difference between system call and procedure call. So I'm taking a look at what is procedure call. Okay, so procedure call as a transfer control. You can also pass a list of parameters along the procedure call. After successful execution, control returns to the initial procedure invoked, and the program continues its execution. By setting the procedure name, listing actual parameters or values within parentheses, and netting a final semicolon. When calling a procedure, we need to be very careful regarding the parameters. Furthermore, the parameter pass for the procedure call should match the original declared parameters. If case there's a mismatch, the compiler throws an error. Okay, so this is the example of procedure call. Here we create a procedure in a program that contains two parameters, first name and last name. Right. Now let's take a look at an example of a procedure call statement. In a distributed architecture, the procedure call may follow additional protocol that allows it to invoke a procedure either remotely or locally. Wait, is it? Is it like calling the function? Is that it? You just check my GitHub and set here you speak bahasa tuh. Oh yes, I'm from Indonesia, so I can speak bahasa Indonesia, I guess. I mean, currently I'm also training to learn speaking English. That's why I'm using English. We are the same. Okay, well, let's learn together then. I mean, that's why I'm doing this live stream, so that anyone who wants to learn together can join in, this is not a tutorial. Alright. I mean, some people think that this is a tutorial, which is not. Oh, no. I'm from Indonesia, not from Philippines. Okay, procedure call. Access locally. Local procedure call, remote procedure call. Local inter-process communication. Wait a minute. Is this the C programming keyword? Let me check. Oh, wait a minute. Procedure and function. Okay, let me check. Oh yeah, I'm a little bit sick right now. Thank you. Okay. In C programming, all executable code resides within a function. Note that other programming languages may distinguish between a function, a subroutine, subprogram. Oh, that other programming languages may distinguish between function, subroutine, subprogram, procedure, or method. In C, let me copy this in the chat in case anyone wants to read this too. These are all functions. Functions are a fundamental feature of any high-level programming language and make it possible to tackle large complicated tasks by breaking tasks into smaller, more manageable pieces of code. At a lower level, a function is nothing more than a memory address where the instruction associated with a function reside in your computer's memory. In the source code, at lower level, a function is nothing more than a memory address where the instruction associated with a function reside in your computer's memory. Okay, what is it called? In C, there is this thing called function pointer. So yeah, it is an instruction that is stored in our computer's memory. In the source code, this memory address is usually given a descriptive name, which programmers can use to call the function and execute the instruction that begin at the function starting address. This memory address is usually given a descriptive name, which programmers can use to call the function and execute the instruction that begin at the function's starting address. That beginning at the function starting address. The instructions associated with a function are frequently referred to as a block of code. Okay. After the function's instruction finish executing, the function can return a value and code execution will resume with the instruction that immediately follows the initial call to the function. If this doesn't make immediate sense to you, don't worry. Understanding what is happening inside your computer at the lowest level can be confusing at first, but will eventually become very intuitive as you develop your C programming skill. For now, it is enough to know that a function and its associated block of code is often executed, called several times from different places during a single execution of a program. This is the basic example. So where is the procedure? Actually, one can use the return keyword in a procedure to return to the color before the end of the procedure. But one cannot return a value as if it were a function. The usage of a function as a procedure. It's a simplistic program that asks students for their grade for 3 different courses and tells them if they pass a course. Here we create a function called check that can be called as many times as we need to. The function saves us from having to write the same set of instructions for each class the student has taken. Okay. Notice that in the program above there is no outcome value for the check function. It only executes a procedure. Is procedure in here means the instruction? How you make procedure in C? Why is it -4? Okay. So I'm new to C and trying to make procedure to swap value of the variable when I run this swap. Didn't work. Which book? Is it the C programming language book? is procedure? No, is it the same? So is it basically executing the instruction? Oh, there is procedure-oriented programming. That is new. Okay, let's great buddy, keep it up. Thank you, Jeff, VRX, and welcome. We are checking out what is procedure in here means. And I didn't know there is this thing called procedure-oriented programming. Oh, this is interesting. POP. Okay. Let me copy this in the chat. If anyone wants to take a look. That emphasize breaking down a program into a set of function or a procedure. These procedures are then executed in a sequential manner to achieve a specific task. It's like following a recipe while cooking. You have a set of instructions or procedures that you need to execute step by step to finish the dish. Let's take a quick look at some key characteristics of procedure-oriented programming. Top-down design, programming paradigm. Okay. Program are designed by breaking them into smaller procedures. Data is shared among functions, leading to potential data security issues. Variable and data type in procedure-oriented programming. To store data, okay, and data type. Is this like functional programming? I'm not sure. Data structure and modularity. Encapsulation of data. Okay. It's like having a well-organized fridge where each ingredient has its designated shelf. Breaking down a problem into functions. It's like deciding between Yeah, this sounds like a functional programming. Let me check. It's a programming paradigm. A high-level way to conceptualize and structure the implementation of a computer program. Programming paradigm, okay. Where programmers construct, say, composing a function, right? Is this the same paradigm? Interesting. What is a procedural? Maybe later. Wait. Oh, wait a minute. This section. Yeah, is procedure call similar to function call? Interesting. Wait and see the result. Let's see. What? The procedure code is then written in the beneath the def statement. Is procedure just a function? I'm not really sure. Why is it different than this one? So which one is correct? I mean, we are using Python, right? the indentation really matter here. So which one is the correct one for the indentation of the first statement here? Was alive. And what is the function that perform a specific task? Function return of value. Oh, so procedure did not have a return value. Is that it? Well, a function can have a return value. I am not sure. Introduction to procedure. Okay, let me copy this in the chat. Bro, at what time do you start stream? I start stream maybe around 5 a.m. in the morning. Yeah, I like to learn early in the morning before life coming down. Before a lot of people wake up. That give me peace, you know. Top-down design. This is the idea that with any problem you should attempt to break down the problem into small manageable tasks. The code for this manageable tasks will now be isolated into what is called a procedure. The code for this manageable tasks will now be isolated into what is called a procedure. And I use procedure interchangeably. This may not always be correct use. Subroutine that can return multiple results through calling argument. A procedure that returns only a single value that is used in the evaluation of an expression. The data that goes into or comes out from a procedure. Okay. Don't repeat code, but we have not seen how to reuse code. A subroutine is a procedure that receives its input value and return its result through an argument list. The general form of a subroutine is some name, some argument list, return. Okay, declaration section, execution section. That looks like a function to me. The variable in the argument list are known as dummy argument because memory is not allocated for them. Rather, they act as placeholder for the actual arguments when the subroutine is called. Actual argument when the subroutine is called. The subroutine itself behaves as a mini program in that it has both a declaration and execution section. When the subroutine is called, control of the program shift from the calling program or subprogram called control of the program. When the subroutine is called, control of the program shift from the calling program or subprogram to the subroutine. Call some name. Where the data type and order must match the dummy argument of the subroutine. Okay. Example of a program that calls a subroutine above. Intent, okay. Where is the procedure? To share data, but also a way to share subroutine. Documentation standard. What? Okay, so maybe the procedure is some kind of, what is it? It's like usual function call, maybe. Remote procedural call. Wait a minute. Let me put this in the chat in case anyone wants to see this. I hope this is big enough to see. Procedural call in computer science refers to the invocation a specific task within the program. we got function on author name. When a procedure is called, okay, let me take notes. The difference between system call and maybe I should simplify this. System call both system call and transfer control from the current instruction another instruction from the caller calling. From the color let me think. Okay. And then terms of operating system. Operating system. But the system call also rising the hardware preference. also raising the hardware performance. Okay, user application run inward is referred to. Okay, already shared this. Okay, let's continue this first. User application run inward is referred to as user mode, which means the hardware restricts what application can do, can typically initiate input-output requests to the disk, access any physical memory page, or send a packet on the network. When a system call is initiated, usually through a special hardware instruction called a trap, the hardware transfer control to a specified trap handler that the operating system set up previously. Special hardware instruction, okay. Specified trap handler that the OS set up previously and simultaneously raise the privilege level to kernel mode. The kernel mode, the operating system has full access to the hardware of the system and thus can do things like initiate an input-output request or make more memory available to a program. When the operating system is done servicing the request, it passes control back to the user via special return from trap instruction, which refers to user mode while simultaneously passing control back to where the application left off. Okay. Return from trap. Okay. When operating system really took off was in the era of computing beyond the mainframe, that of the mini computer. Classic machine like PDP family from digital equipment made computers usually more affordable. Thus, instead of having one mainframe per large organization, now a smaller collection of people within an organization could likely have their own computer. Not surprisingly, one of the major impacts of this drop in cost was an increase in developer activity. More smart people got their hands on computer and thus made computer systems do more interesting and beautiful things. Drop in cost was an increase in developer activity. Increase in developer activity. More smart people got their hands on computer and thus made computer systems do more interesting and beautiful things. In particular, multi-programming became commonplace due to the desire to make better use of machine resources. Instead of just running one job at a time, the operating system would load a number of jobs into memory and switch rapidly between them. Thus improving CPU utilization. data to decide to make better use of machine resource. Multi-programming. One job at a time would load a number of jobs. Okay. This switching was particularly important because input-output devices were slow. Having a program wait on the CPU while its input-output was being serviced was a waste of CPU time. Okay. Instead, why not switch to another job and run it for a while? Well, I'm kind of curious. If we are switching, what is it called? If the CPU switching to another job, what happened to the process from the previous job? Do we save the state of the, what is it called? The previous process, maybe? See, wait on the CPU while input-output being serviced. Right. Maybe the book will answer that question. We will see the desire to support multi-programming and overlap in the presence of input-output and interrupts force innovation in the conceptual development of operating system along a number of directions. Issues such as memory protection become important. In the presence of input, output, and interrupt force innovation in the conceptual development operating system along a number of directions. Issues such as memory protection become important. We wouldn't want one program to be able to access the memory of another program. Wait a minute, let me take notes of my question earlier. What happened? To the current process? If we switch to another process, if we make the CPU switch to another process. Become important. The memory protection become important. We wouldn't want one program to be able to access the memory of another program. Understanding how to deal with concurrency issues introduced by understanding how to deal with concurrency issues introduced by multi-programming was also critical. Making sure the operating system was behaving correctly, despite the presence of interrupts, is a great challenge. Okay, maybe the answer to my previous question is what happened when we switch to another process, right? What happened to the current process if we switch to another process? Maybe we will get an answer in the concurrency section or chapter. We will see the presence of interrupts. When we are switching to another job or process, we are basically, what is it called? We are basically interrupting the current process, right? As far as I understand. While waiting for something to be done, we are doing another thing. Like, what is it called? Like take hold or something like that. Yeah, I'm still not really sure. Maybe we will get an answer in the concurrency section. Okay, we will study these issues and related topics later in the book. One of the major practical advances of the time was the introduction of unique operating system, primarily thanks to Ken Thompson and Dennis Ritchie at Bell Labs. Practical event of the time. Yes, the phone company. Unix took many good ideas from different operating systems, particularly from Multics, and some of the system like, oh, I didn't know about this. Then next, okay, and the Berkeley time sharing system, okay, but made them simpler and easier to use. Soon this team was shipping tapes containing unique source code to people around the world, many of whom then got involved and added to the system themselves. See the aside next page for more detail. The modern era, okay, well, let me read this first. We'll use asides and other related text box to call attention to various items that don't quite fit the main flow of the text. Sometimes we'll even use them just to make a joke. Because why not have a little fun along the way, right? Having fun along the way. Yes, many of the jokes are bad. At least the author admit this. Okay, it is commendable. Anyway, the modern era. Beyond the mini computers came a new type of machine. Cheaper, faster, and for the masses. The personal computer, or PC, as we call it today, made by Apple's early machine, okay, and the IBM PC, this new breed of machine, What soon become the dominant force in computing? Oh, this is the aside. Okay. Maybe we will read that after finishing this section. In computing, as the low cost enable one machine per desktop instead of set mini computer per work group. Unfortunately for operating system, the PC at first represent a greatly backward. Oh, greatly backward, as early system forgot or never knew of the lesson learned in the era of mini computers. For example, early operating systems such as DOS, Disk Operating System, from Microsoft, didn't think memory protection was important. Thus a malicious or perhaps just poorly programmed, application could scribble all over. There is another aside, scribble all over memory. The first generation of Mac OS, version 9 and earlier, took a cooperative approach to job scheduling. Thus a thread that accidentally got stuck in an infinite loop could take over the entire system, forcing a reboot. The painful list of operating system features missing in this generation of system is long and too long for a full discussion here. Fortunately, after some years of suffering, the old features of mini computer operating systems started to find their way onto the desktop. For example, Mac OS X. Mac OS has Unix at its core, including all of the features one would expect from such a major system. Windows has similarly adopted many of the great ideas in computing history, starting in particular with Windows NT, a great leap forward in Microsoft operating system technology. Even today's cell phone run operating system that are much such as Linux that are much more like what a mini computer ran in the 1970s than what a PC ran in the 1980s. Thank goodness. It is good to see that the good ideas developed in the heyday of operating system development have found their way into the modern world. Even better is that these ideas continue to develop, providing more features and making modern system even better for users and applications. Summary. Let me read this first. Aside. Maybe we will continue this on the next session. So that's it for now. Thank you for watching and see you next time. Bye bye.